Welcome to The Explainer. Today, we're going to talk about something you probably learned back in middle school, but it turns out this one simple idea is secretly running the show behind everything from roller coaster safety to, believe it or not, the fundamental laws of geometry.
All right, so let's start with a little puzzle. What do you think a roller coaster height limit, the runtime of an algorithm on your computer, and even the very shape of the universe all have in common?
The answer, you might be surprised, isn't some super complex high-level theory. Nope, it's a really simple tool, something for comparison that literally defines the absolute boundaries of what is possible. And that answer is inequalities.
Okay, so to really get their power, we've got to start with the basics. What are these things really?
It's pretty simple, actually. You know how an equation is all about perfect balance, right? Both sides are exactly equal? Well, an inequality is about everything else. It's for defining a relationship that isn't balanced, where one side is bigger or smaller than the other.
So first up, we've got this strict inequalities, less than and greater than. And that word strict is key here. It means the two sides can get ridiculously, infinitesimally close, but they can never, ever be equal.
And you know these symbols we see all the time? You'd think they're ancient, right? Like from Roman times or something? Well, nope. They only first showed up in print in 1631 in a book by a mathematician named Thomas Harriot. He used them to say, pretty simply, A is greater than B.
And get this, there's a really cool story that suggests Harriot might have gotten the idea while he was surveying North America. Apparently, he saw a similar-looking symbol on a Native American's arm and adapted it. How wild is that?
Then you just add one little line underneath and boom, you get the non-strict inequalities, less than or equal to, and greater than or equal to. And that tiny little line, it changes everything. It opens up the possibility that the two sides could be a perfect match.
Okay, so knowing the symbols is step one. But the real power, that comes from knowing the rules of the game.
And honestly, for the most part, the rules are super simple. Just like with regular equations, you can add or subtract the same number from both sides, no problem. Same with multiplying or dividing by a positive number. The relationship holds true. But there is one crucial, tricky exception. And this is the one that gets everybody.
So let's take a simple example. If 2x is less than 8, it just makes sense that x has to be less than 4, right? We just divide both sides by a positive 2 and nothing weird happens. The sign stays the same.
But this is where that special rule comes into play. What happens when you use a negative number? Well, multiplying or dividing by a negative, it flips the whole thing right on its head.
So check this out. If negative 2x is less than 8, and we divide both sides by negative 2, x suddenly becomes greater than negative 4. See? The sign completely flips around. You have to flip the inequality sign. That is the one golden rule you can't forget.
All right, and this is where inequalities, for me, get really cool. They're not just about one single number or one answer. They're about a whole universe of possibilities. And the best part? We can actually draw a picture of that universe.
Yeah, graphing them is actually a pretty straightforward three-step process. First, you draw the line. Think of it like a fence that separates all the yes answers from all the no answers. Then you just shade in the entire region of possibilities, all the spots that make your inequality true.
Let's just run through a quick example so you can see exactly how it works.
Okay, so first things first, we plot the boundary line, just like it was a regular old equation. And because our inequality has that or equal to part, we draw a solid line. That means every single point on that line is a valid solution.
All right, next up, since y is less than or equal to the line, we shade everything below it. And this huge shaded area, this represents an infinite number of points, an infinite set of solutions that all make the inequality true. Pretty cool, huh?
So now that we have the rules down, let's see how these simple ideas actually create fundamental laws in the real physical world. And we'll start with something super basic. The triangle.
This right here, this is one of the most important fundamental rules in all of geometry. And it's just a simple inequality. It says that the sum of any two sides of a triangle has to be greater than the third side. This isn't just a math rule. It's a physical constraint on reality itself. So let's put this to the test real quick. Imagine you've got 3 sticks, and their lengths are 3, 4, and 9. Can you actually connect them end to end to make a triangle? No way, not a chance. And the theorem gives us the answer instantly. Look, 3 plus 4 is 7, and 7 is not greater than 9. The two shorter sides wouldn't even be long enough to touch. So you see, it's not just some abstract rule in a textbook, it's a hard physical limitation of the space we live in.
Okay, now for what I think is one of the absolute coolest and most powerful uses for inequalities, making guaranteed predictions, even when you're missing almost all of the information.
I mean, think about it. In the real world, you almost never have perfect information, right? Certainty is super rare. But what if you could draw a line in the sand and say, look, I don't know the exact answer, but I can absolutely guarantee you it's not going to be more than this. Well, that's exactly what inequalities let us do with probability.
And our first tool for this is something called Markov's inequality. And the magic of this thing is that it needs almost no information to work. All you need to know is that a value can't be negative, and you need to know its average. That's it. With just those two things, you can start making some rock-solid, guaranteed predictions.
So here's a classic example to show you what I mean. Let's say there's an exam. It's graded out of 100, and the only thing we know is that the class average was a 25. Now, without seeing a single person's score, can we figure out anything about how many students got a perfect 100?
You bet we can. Markov's inequality gives us a hard limit. The average is 25, and a perfect score is 100. So it tells us that at the absolute most, only 1/4 of the class could have gotten that perfect score. If even one more student got 100, it would be mathematically impossible for the average to be as low as 25.
So Markov's is pretty powerful, but we can actually do even better. We just need one more piece of information, something called variance. You can just think of it as a measure of how spread out the scores are. If the variance is low, it means most scores were clumped together near the average. If it's high, they were all over the place.
And knowing that brings us to our next tool, Chebyshev's inequality. By using both the average and the variance, it lets us draw a much tighter, more precise boundary. So for that exam example, instead of saying at most 1/4 of the class got 100, Chebyshev's might let us say at most 1/10 of them did. It's a more informed prediction with an even stronger guarantee. So when you look at all of this, from just simple comparisons all the way to the laws of geometry and making predictions about probability, you start to see what inequalities really are. They're the language we use to describe limits. They don't always give you an exact answer, but they often give you something way more powerful. They give you the boundaries of what's possible.
They define what can happen, what can't happen, and what's absolutely guaranteed. So from the shortest path between 2 points to the odds of a rare event, how many inequalities are shaping the world around you right now? Thanks for joining the Explainer.